The Permian period, spanning from 299 to 252 million years ago, was a time of striking contrasts in Earth's history. While we often associate prehistoric dangers with the era of dinosaurs, the Permian world held its own set of incredible challenges for land-dwelling creatures. Picture a landscape dominated by a single massive supercontinent surrounded by vast oceans. This was Pangaea, a world alien to our modern eyes. The oceans teemed with diverse marine life, but it was on land where a dramatic evolutionary story unfolded. During this time, the terrestrial environment was home to an array of formidable predators that would rival even the most fearsome dinosaurs in their ability to inspire fear. These creatures shaped the course of evolution through their hunting prowess and adaptations to the harsh Permian conditions. As we explore this ancient world, we'll uncover the fascinating dynamics between predators and prey, the unique adaptations that allowed some species to thrive, and the eventual fate of this remarkable ecosystem. The Permian period holds many surprises, and its story is crucial to understanding the development of life on Earth as we know it today. While the land was a battleground of tooth and claw, the oceans held a surprising secret. How did the formation of a single landmass create such contrasting environments, making the seas a relative haven compared to the perilous terrain above? The Permian period, lasting from approximately 299 to 252 million years ago, was a time of extreme geological and climatic changes that reshaped the face of the Earth. This era saw the formation of Pangaea, a supercontinent that united all of Earth's land masses into one colossal body. The creation of Pangaea had profound effects on the planet's climate and ecosystems, setting the stage for a world unlike any we've seen since. Imagine a vast, unbroken landmass stretching from pole to pole, surrounded by a single enormous ocean called Pangaea. This superocean played a crucial role in moderating global climates, distributing heat and nutrients across the planet. However, Pangaea's formation drastically altered global weather patterns. The interior of the supercontinent became increasingly arid, with extreme temperature fluctuations between scorching days and freezing nights. Massive deserts expanded, covering large swaths of land, while the coasts experienced intense monsoon seasons. These harsh conditions on land created a challenging environment for terrestrial life. Plants and animals had to adapt to survive in a world of extremes. The arid climate led to the evolution of more drought-resistant plants, including conifers and seed ferns. These plants, with their ability to store water and reproduce through seeds, began to outcompete the moisture-dependent ferns and club mosses that had dominated earlier periods. This shift in vegetation had a significant impact on terrestrial fauna, altering food sources and habitats. Animals developed new strategies to cope with the scarcity of water and food. Early reptiles evolved moisture-retaining skin, a crucial adaptation that allowed them to thrive in arid environments and outcompete amphibians. This development led to a transformation and decline of amphibian habitats as reptiles became increasingly dominant on land. The environmental pressure became a driving force for evolutionary innovation, pushing life on land to new extremes. In stark contrast to the harsh terrestrial conditions, the vast Pangaea Ocean provided a more stable environment. The sheer size of this global ocean helped moderate temperatures and distribute nutrients more evenly. While the land was experiencing dramatic climate shifts, the oceans remained relatively calm and consistent, offering a refuge for marine life. The marine ecosystems of the Permian period were incredibly diverse. Coral reefs flourished, providing habitats for a wide variety of creatures. The oceans teemed with ancient fish, including early sharks and ray-finned fish that would eventually give rise to most modern fish species. Ammonites, with their distinctive spiral shells, were abundant, as were various species of nautiloids. The seas were also home to large marine reptiles like Mesosaurus, an early example of reptiles returning to an aquatic lifestyle. Back on land, the challenging environment was shaping the course of terrestrial evolution. The Permian saw the rise of synapsids, a group of animals that would eventually give rise to mammals. These early mammal-like reptiles, such as Dimetrodon, were among the first large land predators. Their appearance marked a significant shift in terrestrial ecosystems, as they were more active and efficient hunters than their predecessors. The evolutionary pressure on land was intense. Animals needed to be faster, stronger, and more adaptable to survive. This arms race of adaptation led to the emergence of more sophisticated predators and prey. Early reptiles developed improved locomotion, allowing them to move more efficiently on land. The pelycosaurs, a group of early synapsids, evolved sail-like structures on their backs. These sails, made of elongated vertebral spines covered in skin, may have helped with temperature regulation in the extreme Permian climate, allowing these animals to be active for longer periods. As the Permian progressed, the stage was set for the dominance of increasingly formidable land predators. The relatively peaceful oceans stood in stark contrast to the ever more dangerous terrestrial realm. This disparity would reach its peak in the late Permian, setting the scene for one of the most dramatic periods in Earth's history. The late Permian's dangerous landscape harbored a predator unlike any seen before. How did a group of animals, starting no larger than a human foot, evolve into some of the most terrifying hunters of their time? Enter the gorgonopsids, Earth's first saber-toothed predators, and the ultimate masters of the Permian terrestrial realm. Gorgonopsids were a group of synapsids, the same lineage that would eventually give rise to mammals. These creatures first appeared around 265 million years ago during the Middle Permian, but their rise to dominance was a gradual process. Initially small and unassuming, gorgonopsids underwent a remarkable transformation as the Permian progressed and environmental pressures intensified. The evolution of gorgonopsids into formidable predators was largely facilitated by the extinction of the dinocephalians, a group of large herbivorous and carnivorous therapsids. With this ecological niche vacant, gorgonopsids seized the opportunity to grow larger and more imposing. Their success was due in large part to their unique adaptations, particularly in their skull and teeth. Gorgonopsids possessed elongated skulls with deep-set eye sockets and a distinctive dentition. They evolved elongated canines and incisors, with some species developing upper canines that were among the largest seen in any non-mammalian therapsid. These saber-like teeth were highly effective weapons for hunting and killing prey. The hunting strategies of gorgonopsids likely resembled those of later saber-toothed mammals, such as Smilodon. They may have targeted the necks of their prey, using their elongated canines to inflict severe damage and induce rapid blood loss. Alternatively, they might have employed a bite-and-run technique, wounding their prey and then following it until it succumbed to its injuries. This approach shares similarities with the hunting methods of some later predators, showcasing the evolutionary continuity of successful predatory strategies. As gorgonopsids diversified and spread, they became the dominant predators across vast swathes of Pangaea. Fossil evidence shows that various species of gorgonopsids inhabited regions that are now parts of Africa, Asia, and Europe. This wide distribution is a testament to their adaptability and success as a group. The diversity within the gorgonopsid family was remarkable. While some species remained relatively small, others grew to impressive sizes. The largest known gorgonopsid, Inostrancevia, could reach lengths of up to 3.5 meters, making it one of the largest land predators of its time. Inostrancevia, with its massive skull and powerful build, would have been a formidable sight in the late Permian landscape. Gorgonopsids thrived in a variety of ecosystems during the late Permian, a period characterized by extreme environmental conditions. From warm floodplains to cold, arid deserts, these predators found ways to survive and dominate. This adaptability allowed them to maintain their position at the top of the food chain across different environments. The success of gorgonopsids had far-reaching effects on Permian ecosystems. As apex predators, they played a crucial role in shaping the evolution of their prey species. Herbivores would have needed to develop new defenses or escape strategies to survive in a world dominated by these efficient hunters. This evolutionary arms race likely contributed to the increasing complexity and diversity of terrestrial life during the late Permian. The evolutionary arms race between predator and prey reached its peak with the emergence of a truly nightmarish creature. Imagine a predator with teeth longer than your hand, specifically designed to slice through flesh and bone. This was inostrancevia, and its hunting prowess would reshape the Permian world. Inostrancevia's extraordinary dental adaptations set it apart from its contemporaries. Its upper canines were massive, measuring up to 15 centimeters in length. These saber-like teeth were curved and serrated, allowing inostrancevia to effectively slice through the flesh of its prey. This dental arsenal could cause massive blood loss and damage to vital organs, making inostrancevia an exceptionally efficient killer. The hunting strategies of inostrancevia have been the subject of much scientific speculation. Current theories suggest two main tactics. One possibility is that it employed a bite-and-run strategy, inflicting severe wounds on its prey and then following it until it succumbed to blood loss. Alternatively, inostrancevia might have targeted the necks of its victims, similar to the hunting method used by modern big cats. However, unlike today's large carnivores, Inostrancevia's oversized canines and powerful jaw muscles were specifically evolved for maximum killing efficiency in a world where survival often depended on the ability to take down large, well-defended prey. The environments Inostrancevia called home were harsh and unforgiving. The late Permian was characterized by extreme climate conditions, with many regions experiencing prolonged dry seasons followed by intense monsoons. These challenging conditions likely contributed to Inostrancevia evolution as a supremely efficient predator, as only the most well-adapted creatures could survive in such an unforgiving world. Inostrancevia potential prey included a variety of herbivorous species that had evolved their own defensive adaptations. One such creature was Scutosaurus, a large, heavily armored reptile. Scutosaurus sported thick bony plates and spikes as protection against predators. However, even these formidable defenses might not have been enough to deter a determined Inostrancevia, with its powerful build and specialized teeth capable of inflicting devastating wounds. The impact of Inostrancevia on Permian ecosystems was profound. As the apex predator in many of its habitats, it would have exerted significant pressure on prey populations, influencing their behavior and evolution. The presence of such a formidable hunter likely drove the development of more effective defensive strategies among herbivores, from improved armor to enhanced speed and agility. This evolutionary arms race contributed to the increasing complexity of terrestrial ecosystems in the late Permian. Rubidgeinae atrox, a formidable member of the rubidgeinae subfamily, emerged as a dominant predator during the late Permian period. With a skull comprising over 15% of its body length, this creature stood out even among its impressive relatives. Growing up to 10 feet, 3 meters long, Rubidgeinae atrox possessed a head nearly twice as large in proportion to its body as a modern lion. The rubidgeinae, including Rubidgeinae atrox, were characterized by their robust skulls, deep-set eye sockets, and most notably, their impressive dentition. Unlike other gorgonopsids, the rubidgeinae developed deeply serrated teeth, which were more effective for cutting through flesh. This dental adaptation set them apart from their relatives and hinted at a specialized hunting strategy. Despite its imposing size, Rubidgeinae atrox had some surprising characteristics. Its bite force, while powerful, was estimated at only 715 newtons, just 20% stronger than that of a modern wolf. This relatively modest bite force, combined with its serrated teeth, suggests that Rubidgeinae atrox was not a bone crusher, but rather specialized in cutting and slicing through soft tissues. The hunting strategies of the rubidgeinae have been the subject of scientific speculation. Given their serrated teeth and relatively weak bite force, these predators likely employed a strategy of inflicting deep, bleeding wounds on their prey. They may have targeted vital areas like the throat or abdomen, using their specialized dentition to cause massive tissue damage and blood loss. This method would have been particularly effective against the large, well-armored herbivores of the late Permian. Comparing the rubidgeinae to other gorgonopsids reveals distinct differences in dental adaptations. While genera like inostrancevia were known for their massive saber-like canines, the rubidgeinae developed a more generalized set of cutting teeth. This variation in dental morphology suggests that these groups of predators may have occupied different ecological niches, perhaps targeting distinct types of prey or employing unique hunting strategies. The rubidgeinae subfamily exhibited remarkable diversity, comprising 9 different genera. These ranged from medium-sized predators to the massive Rubidgeia atrox. This diversity allowed the rubidgeinae to occupy various ecological roles within their environments, from pursuing smaller, faster prey to taking down large herbivores. The presence of multiple genera within the same subfamily indicates a highly successful evolutionary lineage that was able to adapt to a range of environmental conditions and prey types. The impact of the rubidgeinae on Permian ecosystems, particularly in Africa, where many of their fossils have been found, was significant. As top predators, they would have exerted strong selective pressures on their prey species, driving the evolution of new defensive adaptations. The presence of multiple large gorgonopsids in the same ecosystems, including both rubidgeinae and other genera like inostrancevia, suggests a highly competitive environment. Herbivores would have faced constant predation pressure, likely leading to the development of more effective defenses or escape strategies. While herbivores evolved defenses against gorgonopsids, a new threat emerged. Imagine a predator with a head as big as a lion's, but a body only the size of a jaguar. This was just one of the many strange and fearsome creatures that made the Permian land a place of constant danger. Enter the therocephalians, another group of synapsid predators that roamed the Permian landscapes alongside gorgonopsids. These creatures, whose name means beast-headed, were diverse and widespread, with fossils found across Russia, Antarctica, Africa, and China. While they shared some similarities with gorgonopsids, therocephalians had their own unique characteristics that set them apart as formidable hunters. Therocephalians had broader, deeper skulls compared to the elongated skulls of gorgonopsids. Their teeth were also distinct, being smaller and straighter than the iconic saber teeth of their cousins. These differences in skull and tooth morphology suggest that therocephalians may have employed different hunting strategies, perhaps relying more on crushing power than the slicing action favored by gorgonopsids. Among the notable therocephalian species was muscarinus, a creature that perfectly embodied the bizarre proportions mentioned earlier. With a body roughly the size of a jaguar but a head as large as a lion's, muscarinus was a striking sight. Its skull was equipped with numerous sharp, conical teeth, making it a highly effective predator. Muscarinus was one of the most abundant therocephalians during the late Permian and may have achieved apex predator status in certain environments, competing directly with gorgonopsids for the top spot in the food chain. A fascinating theory adds another layer of complexity to these already fearsome creatures. Some scientists have proposed that certain therocephalians, particularly some species of ichthyosaurs, may have been venomous. If true, this would make them the first venomous tetrapods in Earth's history. While this theory is still debated within the paleontological community, it highlights the potential for even more specialized adaptations among Permian predators. The dangers of Permian land extended beyond synapsids. Protosuchians, early crocodile-like reptiles, also stalked the landscape. These predators were equipped with large, needle-like teeth, suggesting a semi-aquatic lifestyle similar to modern crocodiles. Protosuchians were found on every continent except Antarctica and North America, indicating their success as a group and their ability to adapt to various environments. The diversity of hunting strategies among these land predators was remarkable. From the slicing action of gorgonopsid saber-teeth to the crushing power of therocephalian jaws and the potential use of venom by some species, Permian predators had evolved a wide array of techniques for subduing prey. This diversity created a complex ecosystem where different predator groups filled various niches. In the Permian food web, gorgonopsids, with their large size and powerful builds, likely targeted larger prey. Therocephalians, with their diverse sizes and adaptations, could have filled multiple roles, from small insectivores to large carnivores competing with gorgonopsids. Protosuchians, with their semi-aquatic lifestyle, may have specialized in ambush predation near water sources, adding another dimension to the Permian landscape. For herbivores, life on Permian land was a constant struggle for survival. With such a diverse array of predators, each with their own hunting specializations, there were few safe havens. This intense predation pressure likely drove the evolution of various defensive adaptations among herbivorous species. From thick armored hides to enhanced speed and agility, prey animals would have needed to continuously evolve to stay ahead in this evolutionary arms race. As Permian land animals engaged in their deadly evolutionary arms race, life in the oceans took an unexpected turn. The seas, once teeming with monstrous predators, had become a relative haven. But what led to this dramatic shift in the balance of power between land and sea? The answer lies in the aftermath of the Capetanian extinction, a significant event that reshaped marine ecosystems. This extinction event had a profound impact on marine life, leading to a decline in the size and diversity of ocean-dwelling creatures. The once dominant large predators of the seas were largely wiped out, leaving behind a world of smaller, less imposing marine animals. In the wake of this extinction, the oceans were left without the massive apex predators that had previously ruled the waves. The largest marine predators of the late Permian were relatively modest in size, typically reaching lengths of around 2 meters, 6.5 feet. For example, the helicoprion, a bizarre shark-like fish with a spiral-toothed jaw, had already vanished by this time. In its place, smaller sharks like the Haycitus became the top predators of the Permian seas. This reduction in predator size and diversity created a stark contrast between marine and terrestrial environments. While land-dwelling creatures faced the constant threat of massive, highly specialized predators like gorgonopsids and therocephalians, marine life enjoyed a comparatively peaceful existence. The absence of large marine predators meant that smaller sea creatures could thrive without the constant fear of being hunted by monstrous leviathans. However, this relative safety came at a cost. The marine biodiversity of the late Permian was significantly lower than in previous eras. Many groups of marine organisms, such as trilobites and ammonoids, had been severely impacted by previous extinction events. Those that remained were often smaller and less diverse than their ancestors. The oceans of this time were characterized by a lack of the spectacular diversity that had marked earlier periods of Earth's history. Despite this reduction in diversity, the Permian oceans still hosted a variety of unique creatures. Smaller sharks continued to patrol the waters, while primitive arthropods scuttled along the sea floor. These creatures, though less imposing than their predecessors, played crucial roles in maintaining the balance of marine ecosystems. Their presence ensured that the oceans remained productive and stable, even as the land above underwent dramatic changes. The evolutionary pressures in these marine environments were markedly different from those on land. While terrestrial animals were locked in an intense evolutionary arms race, driven by the need to either hunt more effectively or avoid being eaten, marine life evolved at a more leisurely pace. The relative stability of the ocean environment allowed for slower, more gradual adaptations rather than the rapid changes seen on land. This stability in marine ecosystems stood in sharp contrast to the volatile conditions on land. As we've seen, terrestrial environments were characterized by extreme temperatures, aridity, and the constant threat of predation. The late Permian world was one of harsh extremes on land, with creatures continually adapting to survive in an unforgiving landscape dominated by fearsome predators. In the oceans, however, life found a sort of equilibrium. Without the pressure of large apex predators, marine ecosystems settled into a new balance. Smaller predators kept prey populations in check, while herbivorous and filter-feeding organisms thrived in the absence of major threats. This created a more stable, if less diverse marine world compared to the chaotic and dangerous terrestrial realm. It's important to note that while the Permian oceans were relatively safer than the land, they were far from paradise. The Capetanian extinction had left its mark, and many marine groups were still struggling to recover. The oceans of this time were in a state of transition, slowly rebuilding their biodiversity in the wake of a major ecological upheaval. As the oceans recovered, land-dwelling creatures faced their own set of challenges. Imagine a world where simply being a plant eater was a dangerous occupation. What kind of adaptations would you need to survive? The Permian period was home to a diverse array of herbivorous animals, each with their own unique adaptations for survival. These plant eaters ranged from small, agile creatures to massive, armored behemoths. Among the notable groups were the dicynodonts, captorhinids, and pariasaurs, each contributing to the complex ecosystem of the time. One key adaptation that many Permian herbivores developed was burrowing behavior. Species like Lystrosaurus, for example, were known to dig burrows as a means of protection from predators and harsh environmental conditions. This adaptation allowed them to escape the scorching heat of the Permian day and avoid detection by the numerous predators that roamed the landscape. The challenges faced by Permian herbivores were not limited to predation. The harsh environmental conditions of the late Permian, characterized by extreme temperatures and aridity, further intensified the struggle for survival. These conditions necessitated the development of specialized adaptations for coping with drought and temperature fluctuations. Some herbivores evolved more efficient digestive systems to extract maximum nutrition from tough, drought-resistant plants. For instance, certain dicynodonts developed specialized jaw structures and tooth arrangements that allowed them to process fibrous vegetation more effectively. Other herbivores might have evolved specialized water conservation mechanisms, such as the ability to concentrate urine or extract moisture from their food, similar to modern desert-dwelling animals. The diversity of herbivores in the Permian period is a testament to the adaptability of life. From small burrowing creatures to massive armored giants, each species found its niche in this challenging world. This variety of forms and strategies allowed herbivores to exploit different food sources and habitats, maximizing their chances of survival in a world dominated by fearsome predators. Some herbivores relied on their size for protection. Others may have developed enhanced sensory capabilities to detect predators from a distance, allowing them to flee before being ambushed. Speed and agility likely became important traits for smaller herbivores, enabling them to outmaneuver larger, more cumbersome predators. Herbivores played a crucial role in Permian ecosystems, forming the foundation of the food web. Their presence and abundance directly influenced the dynamics of predator-prey relationships and shaped the overall ecological landscape. As primary consumers, they were responsible for converting plant matter into energy that could be utilized by higher trophic levels. This made them essential components of the Permian biosphere, despite the constant dangers they faced. Despite their adaptations, life for Permian herbivores was a constant struggle. The combination of predator pressure and harsh environmental conditions meant that every day was a battle for survival. This intense selection pressure likely contributed to the rapid evolution and diversification of herbivorous species throughout the Permian period. While herbivores and carnivores engaged in their evolutionary arms race, an unprecedented threat was silently building. Imagine a world where the greatest danger wasn't tooth or claw, but the very air you breathed. What could turn Earth into a planet more hostile than any predator? The answer lies in the Permian Triassic extinction event, also known as the Great Dying. This cataclysmic occurrence, which took place around 252 million years ago, stands as the most severe mass extinction in Earth's history. The scale of this event was so immense that it reshaped the course of evolution and fundamentally altered the planet's ecosystems. The primary suspect behind this global catastrophe was a series of massive volcanic eruptions that created the Siberian traps. These eruptions released enormous amounts of carbon dioxide and sulfur into the atmosphere, triggering a cascade of environmental changes. The sheer volume of greenhouse gases pumped into the air led to severe global warming, with average temperatures potentially rising to levels comparable to Death Valley's hottest months. This rapid and extreme warming had devastating effects on both terrestrial and marine environments. On land, the increased temperatures led to widespread drought and desertification. Forests withered, and once lush landscapes turned into barren wastelands. In the oceans, the warming caused a decrease in oxygen levels, a phenomenon known as hypoxia. This made it difficult for marine life to survive, particularly in deeper waters. The impact of the Permian Triassic extinction on Earth's biodiversity was staggering. It's estimated that approximately 95% of marine species and 70% of terrestrial vertebrate species went extinct. To put this into perspective, the event was far more severe than the later Cretaceous-Paleogene extinction that wiped out the dinosaurs. While the dinosaur extinction eliminated about 17% of biological families, the Permian Triassic event resulted in the loss of approximately 57% of biological families and 83% of genera. Marine ecosystems were particularly hard hit. The warming and acidification of the oceans led to the collapse of entire food chains. Coral reefs, which had thrived in the Permian seas, were almost completely wiped out. Many groups of marine organisms that had dominated the oceans for millions of years, such as trilobites and many species of brachiopods, disappeared entirely. On land, the story was equally grim. The harsh environmental conditions proved too much for many terrestrial species to handle. Even the fearsome predators that had ruled the Permian landscapes, like the gorgonopsids and thermocephalians, couldn't survive the changing world. The once diverse ecosystems of Pangaea were reduced to a fraction of their former complexity. The aftermath of the Permian Triassic extinction was a world drastically different from what came before. With so many ecological niches suddenly empty, the stage was set for new groups of organisms to rise to prominence. This period marked the beginning of the Age of Reptiles, as early reptiles and therapsids, ancestors of mammals, began to diversify and fill the roles left vacant by the extinct species. One group that benefited from this new world order was the archosaurs, which includes the ancestors of crocodiles, pterosaurs, and dinosaurs. These creatures were able to adapt to the harsh post-extinction environment and would go on to dominate terrestrial ecosystems for much of the Mesozoic era. The Permian Triassic extinction event serves as a stark reminder of the fragility of life on Earth. It demonstrates how global environmental changes can have far-reaching and long-lasting impacts on biodiversity. The event reshaped the course of evolution, setting the stage for the rise of new dominant species and ultimately leading to the world we know today. The Permian period marked a critical juncture in Earth's history, characterized by intense evolutionary pressures on land-dwelling creatures. Predators like gorgonopsids and thermocephalians pushed herbivores to develop increasingly sophisticated defenses, driving an arms race that shaped the trajectory of terrestrial life. This period of rapid adaptation and diversification set the stage for future evolutionary developments. However, the thriving ecosystems of the Permian were poised on the edge of a global catastrophe. The impending Permian Triassic extinction event would soon decimate life on Earth, wiping out an estimated 95% of marine species and 70% of terrestrial vertebrate species. This mass extinction, the most severe in Earth's history, cleared the ecological slate and paved the way for the rise of new lineages. The Permian's legacy serves as a stark reminder of life's resilience and adaptability, even in the face of near-total environmental collapse.